Hey there, it's Leanne Gisler. I'm going to talk to you today about a shift register. This is a pretty unique one. I have a bulb out, so I apologize for that. But you can see there that we're running lights off of this shift register, which is going to change parallel and um, series circuits. Sorry, I got that wrong. Parallel and series circuits. You can see here that it has 8 ports. It's hard to see, but I'll explain the sketch and how it has those 8 ports and then how it can be used as an output device. And so it will read and you can make it do things like this, often used in things like boards that will tell words all the way across. It kind of reminds me of how a microbit is set. I'm not real sure about that, but I'm thinking that that's kind of how that microbit is set with those 25 LEDs that you can make words with. Anyway, I'll explain it in the next step. This utilizes an integrated circuit, which adds 8 more pins to the SIK breadboard by only utilizing 3 pins. So that's a pretty cool thing. We are going to use this to drive 8 LED lights. So as you can see in the setup here, we have 4 red lights. The negative ends are facing down on this end. Positive ends are facing the other way. You can identify these through their short or long legs, or by the fact that the negative end is always the flat end of the bulb. They are connected to 330 330 ohm resistors, each one. The yellow lights are just set up just like them, and they're also connected to those 330 ohm resistors. The wiring for this, you can see that each of these red LED lights is wired in here with this wire on this end, this wire on this end, and this wire here. And then this last red one, of course, comes all the way around to here. But they are wired into this integrated circuit. And then your yellow lights are here, here, and here, and here. You can see them all here. And then you have your red that connects here, your blue that connects here all the way to pin 2, your yellow here that connects all the way to pin 4, and your green that connects all the way here to pin 3. You have a ground pin here that goes out and a ground pin here that goes out. You have a power source here that goes here, of course, connects all the way here and all the way around to the 5-volt power. You have a ground source that connects here all the way around to here and all the way to here and around to your ground source here. And that is the basic setup of this shift register. It talks about the IPC or IC, excuse me. And then it talks about how you have to define the pins on the specific one that we have called a serial peripheral interface, or SPI. The 3 pins are the interior data pin number 2, interior clock pin number 3, and interior latch pin number 4. There's also declared a global pin for the data, and we are set up to byte data equals 0, and could be 0 or 1, but this is 0. For the setup, the data pin, which is in 2, is output. The clock pin in 3 is output, and the latch pin in 4 is output. In the loop, you could have one after another, or you could have taken these out, added them back over to here and done one at a time. You could have done ping pong. You could have done random LED. You could have done random marquee or random binary count. And it was encouraged that you try them all. But for the sake of time on this video, I'm going to show you how one after another worked, because that's what my video is about. So you have to make the shift register outputs high or low. So you do void shift right, which is similar to digital right, in desired pin, Boolean desired state. So the bit right data, desired pin, desired state. You change your bit to 0 or 1 in data, and then you set your data to the shift register. So shift out, data pin, clock pin, MSB first data, send the data to the shift register. And then you toggle the latch pin to make data appear at the outputs by doing digital write latch pin high, digital write latch pin low. Now to do the function that I did for the one that I have the video of, void one after another, This will allow them to run one after the other, first the red, then the yellow, then the red, then the yellow. And you have to set this up. So your delay time between them is 100 milliseconds, and you'll turn all the LEDs on for an index equals 0 or an index less than or equal to 7, index plus plus, shift right index high, and then the delay time is set at 100 milliseconds. You'll then have all of them turned off for this scenario of index equals 7, index is greater than or equal to 0, and index minus minus, shift right index low, which means off, and then delay time, which is 100 milliseconds. This was the one at a time, similar setup, but instead it's just one at a time rather than one after another. So it would just be blink 1, blink 2, blink 3, like that. And you can see how that goes there. And then if you have ping pong, which allows them to go one at a time in both directions. You see there, delay time still the same, but you're just setting it for ping pong versus the other. Very similar in the way that things go here. Random LED, which randomly turns them on or off. You're going to set it to index random 8. So you pick a random number there that the microcontroller will pick for you. So the void marquee, I don't know why I said void, but the marquee, this function will mimic chasing lights, like those around signs. Your delay time has to increase a little to 200 seconds or double its time, 200 milliseconds. And then you see how this works, that you're going to index equals 0, index is equal to less than or equal to 3, index plus plus. You tell it to turn it on. And then here's where you tell it to skip 4 and then turn that LED on. And then you use the delay time to slow down the sequence. And then you index low to turn both LEDs off. And then you index plus 4 to turn them off. So you skip 4 and turn off. Then you have binary count, and this creates a visual representation of an on-off pattern bits in a byte. And interior delay time is 1,000 milliseconds. Shift out data pin, clock pin, SB first data, and to send your data byte to the shift register. And then you're going to toggle the latch pin to make the data appear at the outputs. Latch pin will high, digital write latch pin low. Add 1 to the data and repeat, because byte can only store numbers from 0 to 255. And so this is where your data plus plus will come in. And then you're going to delay so you can see what's going on, and according to your delay time, which is 1,000 milliseconds. And that is it. But again, the video that you will see at the very end is one after another, because I built that one and I thought that one was really neat. And so did my students when I showed it to them.